Thank you. Oh, hang on. All right. I think this is working. Oh gosh, maybe not. Okay. There might be like a lot of unnecessary recording at the beginning here. I didn't need to do that. Okay. All right. So we're starting unit 4. Unit 4 is about chemical reactions. It's kind of like why we're actually studying chemistry. We get to talk about the interesting parts of chemistry now. This first intro here, we're going to go over physical changes versus chemical changes. So a physical change is when there is no change in the chemical identity of a substance. Oh gosh. My handwriting is really bad. So if you have like water, liquid H2O, and you were to freeze it, say, make an ice cube, it's still H2O. You have not actually changed the chemical identity. So that would be a physical change. Same thing if you were to like mix the water with something that it doesn't react with. The water is still fundamentally H2O. So no change in the chemical identity. A chemical change is when there is change in a chemical identity, obviously. This is like also a chemical reaction. When you have a chemical change, it's because a chemical reaction is taking place. So if you were to take the water from before and decompose it into hydrogen gas and oxygen gas, now you have different substances on a chemical level, and that would be a chemical change taking place or a chemical reaction. That's like pretty much what we're focusing on this unit. Physical change is not actually important. Some signs that a chemical reaction is occurring. First one is gas production. So if you have, other than boiling a substance, if you have a reaction that's producing a gas, say you're decomposing the water into hydrogen and oxygen gas, you'll see that gas bubbling out of the solution. And that pretty much always means that you have a chemical reaction occurring. You're creating a substance that is now a gas at whatever temperature rather than whatever you had before, which was a liquid or a solid. Another sign of a chemical reaction is precipitation. I think we've talked about this a little bit already. But precipitation is when you have a solid form, usually out of solution, mixing ionic compounds in solution, and you have a solid forming or precipitating out. That's another sign that you have a chemical reaction occurring. You've created a new substance that is no longer soluble, and so it precipitates. Another sign, I just realized I'm going like down 1, 3, 5, 2, 4, 6, but it's fine. Another sign is temperature change. Some chemical reactions will produce heat, others will consume heat. And so you'll witness the temperature of your substance changing. Temperature change, not just temperature. Another sign is a color change. Obviously, if you like mix a pigment into something, it's changing color and that's not a chemical reaction. But if you're mixing solutions that previously didn't have a color and suddenly you're seeing color appear, that's probably because you've created a new compound that has a specific color. Second to last one is it odor production, or creating a new substance that smells strongly of something or other. And then the final one is seeing light or fire or some sort of an explosion. Those are the fun reactions, but pretty much that means you have a combustion reaction. Yeah, look.
What exactly is color in the context of chemistry?
Color has to do with like the chemical nature of the substance and what wavelengths of light it reflects, as well as like what wavelengths of light it absorbs and then produces. When we're talking about like the photons being excited or the electrons being excited and then dropping back down and releasing up photons of specific wavelengths, that's creating light of specific colors. Basically seeing a new color that you didn't have before means you have a new substance that has different chemical properties and is reflecting different frequencies of light. Okay. Yes.
So when it says it's chemical identity, would that be like
those are like chemical characteristics of a substance, yes. When I say chemical identity, really what I mean is like the chemical formula. So like chemical identity of a water when you have it is H2O. That is like fundamentally what the water is made of. And so when you change the chemical identity, you're changing like actually what the molecules of the substance are.
So like if you had H2O plus O and then you got H2O2 or whatever.
Right, then you've changed the chemical identity. It's no longer H2O, it's H2O2 or hydrogen peroxide. Okay. This is frustrating that my iPad keeps turning off. But, okay, so we're gonna get on to how you would actually write a chemical reaction. The first thing here is just the definition of a chemical reaction. A chemical reaction is the rearrangement of atoms by breaking old bonds and forming new bonds. So whatever your reactants are, they'll often be split apart, the old chemical bonds being broken and forming new bonds, creating new different molecules. So when we write a chemical reaction, we write it with the reactants on the left side and then an arrow to the products. This is pretty intuitive. One thing you should note is that a single arrow like this means that the reaction only proceeds in one direction. It only reacts forward, or the reactants form the products, but the products are not being split apart and reforming the reactants at all. If you see a double arrow between the products and the reactants here, that means you have a reaction that is in equilibrium, which is something we'll talk about a lot more later. But basically, the reaction is proceeding forward and backwards simultaneously. The reactants are becoming products and the products are also being split apart and becoming reactants again. That's not too important, but it's something to know about the notation. So here, this is just a good graphic to look at. We have coefficients for each of the molecules, which are the number of those molecules. We have the actual molecules, like the H2 or the O2. And then we also have the physical state of the reactants and the products. In this case, they're all gases, that G with the parentheses around it. Gases. We'll talk more about all these symbols. So chemists use chemical reactions to model the chemical transformations. That's kind of obvious, but there you go. It's a way of notating what's occurring and recording the compounds that are reacting and how much of each compound is reacting, as well as states of matter and whatever else you include. So some of the symbols that are used, you'll see a triangle like that, or a delta sign. Sometimes that's used as change. In a chemical reaction, you'll often see it represent heat or energy being either produced or consumed. Also, if you see RT, that is indicating that the reaction occurs at room temperature. These symbols for states of matter, solid, liquid, gas, are pretty straightforward. And then if you see AQ, that means aqueous solution, or the reactant is dissolved in water. We went over these arrows earlier. A forward arrow means forward only. Multi-directional arrows, forward and a back, means that the reaction is in equilibrium. And then finally, if you see an arrow with some sort of a chemical compound written above it, in this case, they just write it as X, but it could be whatever chemical compound, that means that that compound is a catalyst in the reaction. A lot of this stuff is not that important at this stage, but it's probably good to have in your notes. Okay. This is important though, the subscripts. Subscripts within a molecule, like within the chemical formula for a molecule, indicate the number of atoms in that compound. So like Na2O, this is saying that there are 2 sodium atoms in that molecule. But a coefficient is representing the number of molecules in the reaction. So if you saw like 2Na plus 3 KOH, this 2 and this 3 are the coefficients for the molecules. So that means that for every 2 sodium atoms, you're reacting 3 molecules of KOH. And actually, the way they want you to talk about it is as a molar ratio. So like this is 2 moles of sodium for every 3 moles of potassium hydroxide. Yeah, molar ratio. This is the molar ratio of atoms in the compound. I'm sorry that my handwriting is so bad. It's like almost as bad as Miss Judy's, and it's unfortunate. Or maybe it's been worse, but you know, we'll get by. Does that all make sense so far? How we write chemical reactions, basically, with the subscripts and the coefficients? Okay. We're gonna move on to translating these word equations into chemical equation notation. We're not going to worry about the coefficients yet. We're going to talk about that in a second. That's balancing the equations. Right here, we're just going to translate this. So the first thing that this says is solid potassium reacts with water. So on the left side, our reactants will be potassium, and we'll put an S in parentheses because it's solid, plus water. Water is almost always a liquid, unless it says otherwise. And that produces hydrogen gas. This is an important point to remember, that hydrogen is diatomic, H2 gas, and aqueous potassium hydroxide. This is another important part. When you write something like this, you have to be sure to write good compounds. So when it says getting ahead of myself. When it says aqueous potassium hydroxide, you have to translate that correctly into chemical symbols because otherwise you are going to get the problem wrong. So potassium hydroxide is an ionic compound. Potassium is a cation that likes to take on a +1 or a 1+ charge, and hydroxide is a polyatomic with a 1- charge. So you'll get KOH is the potassium hydroxide, and they say it's aqueous. So we will write that. Sweet.
Charlie,
Yes.
what would be an example of doing that with like a bad?
Well, if instead of like potassium hydroxide, it was say calcium hydroxide, calcium wants a 2+ charge. If you just wrote CaOH, that would be wrong because you would have the OH that wants 1- charge, but the calcium wants a 2+ charge. So the correct chemical formula for calcium hydroxide is CaOH2, or you would write it as OH in parentheses 2, because you need 2 of those. All right, we're gonna do one more and then have you guys do one on your own. That's a good point. We're gonna get to that. That's the balancing the chemical reactions. That's when you include the coefficients, the number of moles of each molecule that you need, exactly. Okay. Yeah, that's an important note. This is unbalanced. Okay, the second one says solid nickel solid reacts with aqueous lead-2 nitrate. This is another important time to think about writing good compounds. So lead-2, lead is a transition metal, which means it can be multivalent or take on different charges. In this case, they tell us it's lead-2, which means it wants a 2+ charge. And nitrate is a polyatomic, NO3-. Pretty sure. If I'm wrong, somebody correct me, but this should be lead. And then because the lead has a 2+ charge and the nitrate has a 1- charge, we need 2 of the nitrates. And when you have a polyatomic, when you have multiple polyatomics, you put the polyatomic in parentheses and then the subscript outside of the parentheses. Okay. That reacts to produce, oh wait, whoops, I forgot, this is aqueous. Reacts to produce an aqueous solution of nickel-2 nitrate and solid lead. So nickel-2 nitrate is going to be very similar to lead-2 nitrate. Aqueous once again, and solid lead. So in this case, we would have the lead precipitating out of the aqueous solution. I believe I have got everything I needed there. This is also still unbalanced. Okay, go ahead and do practice 3 on your own. Go ahead and try and translate that into a chemical equation, and then we'll go over it real quick. Joy, how long is this class? Or like, when does it end, do you know? 05. All right, we have like a lot of time. Yeah, I can't figure out if I'm like going too fast or too slow or what, but. What? I feel like I think I'm about halfway through. Translating word equations, and I get to actually balancing abilities. Freaking out. And then particular diagram.
Oh, it's really just one oxygen. You don't know what monoxide is? Or like monoxide?
We got it. Wait, I don't think that's right.
What else would it be, Ava?
I don't know. But if it's right,
Probably wrong.
that's just embarrassing for you.
Yeah, what's embarrassing for you? You want to talk about it? You know what water is?
I do know what water is, thanks.
Why'd you put a gas next to the water?
Because it's fake.
Oh, okay. I wasn't reading the proper.
Yeah.
And then, oh shoot, I forget the equation for ammonia. Do you remember that?
Yeah, but I'm just not getting funny because you're funny.
Yeah.
Okay, you just don't know it.
No, I don't. Wait, no, hold on.
You don't know that.
What's it again? No. Actually, NH3.
I don't trust you.
No, it is, right?
Yeah.
It is. Yeah.
Okay. Yeah, you're so smart, man.
I'm so smart. You are such a loser.
Yeah.
You're like those people who just run away from the polar bear.
Anyway, and oxygen.
Or the lady who got attacked by a moose. That would be you, Ava. You would almost die by a moose.
That's a good way to go.
Moose. Okay. Yeah. You would never just find a single oxygen.
It's always okay.
Girl.
What?
Static talk.
Okay, I don't know.
So like, when have you ever seen O in your entire life?
Okay, I don't know.
Like, you just O's in there. Like, no, like, O's.
Okay, okay. On the periodic table, it is oxygen, and it is
Oh,
one O.
everything has just a one. Ava.
Yeah, and it's called oxygen. So excuse me if it's oxygen.
Nitrogen
It's not one
oxygen
O.
is just oxygen. Like,
All right.
nitrogen is also nitrogen.
I
Would
would
you call it
call it
nitrogen?
Is that good?
We have some
Is
questions
everybody pretty
thus
much
far.
done?
Feel free to ask our TAs those questions. Thank you. Maybe someone. is
I'm gonna
kind of,
assume we're pretty
you
much
know,
done.
it's a little bit nebulous to you, or there's a concept you don't understand. Feel free to ask.
Does someone want to share what they got? Is anyone relatively confident in their answer?
Ava.
Hayden, Liam, whoever?
I can say. I got NOG plus H2O, G reacts and NH3G plus O2.
Yeah, not OG. One oxygen.
O2 gas. Sweet. Look. Yeah. Oh, I thought that was a question. High five. Sweet. Okay. That looks good to me. So now we get to balance them. This is the slightly more difficult part. These are both still in here, aren't they? Do your copies of the notes have the law of conservation of energy as well as mass?
Yes.
Does it just say law of conservation of mass?
Yes.
Yeah, okay.
Okay, mine's the other. Mine's the other.
The energy is pretty much useless. Law of conservation of energy was in here for some reason. I mean, it's a valid law, but it's not actually relevant. So the important rule when we're talking about balancing chemical equations is the law of conservation of mass. I'm sure you have all heard it before. Mass is neither created or destroyed. Well, it's still abiding by the law of conservation of energy. It's just not important to what we're doing right now. So basically this means, I think it was Hayden had a good point earlier, like we started with 2 hydrogens and we ended up with 3, and that's pretty much just not possible. So when you're balancing, you have to have the same number of each type of atom at the beginning as you have at the end. If you start with 3 hydrogens, you're going to have 3 hydrogens at the end. We're not changing what kind of atoms we have in this class anyway. So when we balance chemical equations, we assign coefficient. That's looks like not what I was writing. We assign coefficients to the molecules in order to abide by the law of conservation of mass. The idea is that if in our original equation we had more hydrogens at the end than we started with, then probably we needed to start with more than one molecule of H2O. So we will fill that in. Basically what we're doing here is we're figuring out, I wrote all these notes and I'm not sure they're really necessary, but we're figuring out how many of each molecule we need to react / we produce. All right. So when you are, these are some useful tips over here. When you're balancing chemical equations, you are only changing the coefficients. You're changing the number of each molecule that you have. You're not changing the subscripts. So if you start changing the subscripts, you're going to end up with bad compounds that don't actually exist. Second tip here is to use the coefficient that results in the lowest common multiple. So when you have a chemical equation, you could always just like do it twice, multiply everything by 2, but when you're writing it, you should go for the lowest common multiple of the coefficients. This final one is balance hydrogens and oxygens last, and in that order, the hydrogens and then the oxygens. That's generally done just because hydrogens and oxygens are all over the place, and if you're balancing the other atoms, you're going to be messing with the number of hydrogens and oxygens you have. So you're going to have to like go back and rebalance the hydrogens and the oxygens. And then the final tip is to make sure that the coefficients are whole numbers. So if they're not whole numbers, that's when you would multiply it by all the coefficients by some number so that you make them whole molecules and not fractions of molecules.
Oh, quick note, this may seem obvious, but they can't be negative. And you also can't do just 0, 0, 0, 0. That would work, but we don't accept that, sorry.
That would be a non-reaction. One other thing, when you are balancing with a polyatomic, you can treat the polyatomic as one unit, but only if it is conserved. Meaning that like, sorry, I'm gonna finish writing and then talk. Okay. That means that like, if you start with a nitrate and in the end, the compound still includes the whole nitrate, you can treat that nitrate as one unit and balance it as if it were just another atom. But if the nitrate is being broken up and the nitrogens and the oxygens are going to different molecules, in that situation, you would have to balance the nitrogens and the oxygens individually.
If what? One unit if, what does it say after if conserved?
Treat the polyatomic as one unit if conserved, sorry. Okay, so balancing equations, how do we actually do this? I'm gonna start with Miss Judy's tedious method because it's a good reliable way to do it. If it makes sense to you and you can just zoom ahead and fill in the coefficients and check it at the end, that's fine too. The way Miss Judy likes to do this though, is that you start by writing down how many of each atom you have in your reactants and how many of each atom you have in your products, assuming that all the coefficients are 1. So right here, we have 1 calcium. We have 2 chlorine. We have 3 sodium. And then this PO4, that's phosphate, and it is conserved. It's still PO4 over here. So we will just treat it as one unit. We have 1 of them. There are not 4 of them. There are 4 oxygens in the phosphate, but only 1 phosphate. And then on the product side, over on the other side of the arrow, we have 3 calcium, 2 phosphate, yeah, that's right, 1 sodium, and 1 chlorine. So once you write this all out, it's probably going to be pretty obvious that some things are wrong. We start with 1 calcium and we need 3. You start with 1 phosphate and we need 2. The way I like to do it is to start on the reactant side and to first look at what reactants you don't have enough of, and then you can go over to the products and look at what products you should be producing more of. So the first thing I see is that we need 3 calciums and we only have 1. So you can multiply this calcium by 3, but because it's in a compound with the chlorine, you're going to have 3 times as many chlorine as well. So we're going to end up with 3 calcium and 6 chlorine. The 6 chlorine is wrong, but for now I'm going to stick with the reactants. The other reactant that we don't have enough of is phosphate. So multiply the phosphate by 2 to get the 2 phosphates over there. We're also going to have to multiply the sodiums by 2 because they are in a compound. 6 sodium, 2 phosphate. So now we have enough of all of our reactants, but we do have too many chlorine and sodium. So you can go over to the right side and we see that we need 6 times as much sodium, and this works out nicely. We need 6 times as much chlorine. So quick check, we have 3 calcium, 6 chlorine, 6 chlorine, 6 sodium, 2 phosphate, and 2 phosphate over there. So now these numbers that you multiplied by become the coefficients. We multiplied this calcium chloride molecule by 3. We multiplied the sodium phosphate molecule by 2. This calcium phosphate was not multiplied by anything. You can write in a 1 or you can leave that blank. And then the sodium chloride was multiplied by 6. So that is how you would balance it, this equation at least. There are quite a few practice problems here. You guys can go ahead and work through these. If you have questions, let me know. There are a bunch here, but I think I'll just let you loose to do all 3 of them. Yeah.
Would we have to go to work or could we just like write it
No.
down?
You could just write it. And this method is not what you have to use. It's just a nice, reliable way to make sure you do it right. If you just like look at it and it's like, oh, we need twice this, then you can just write it in. But yeah, go ahead and do practice 2, 3, 4. This is kind of an important skill, kind of a foundational one that you're going to use a lot. It's not going to be the focus of problems generally, but it's important to know how to do this right. Yeah. Does that mean I didn't have to do all the recording stuff? All right. Well, particulate diagrams. This is another way to represent a chemical reaction. You'll see the reactants drawn on the left, and that's definitely, and yes, it's supposed to be an arrow, and the products on the right. This pen is very shaky indeed. You'll see that then this arrow, this is a single direction reaction. There's a single arrow, not an arrow in both directions. And then in this case, there's a little key. Sometimes they won't give you a key and you'll just have to figure it out without actually knowing what the molecules are. But in this case, the blue are hydrogen, black are carbon, and the red are oxygen. So we have diatomic oxygen reacting with CH4, methane, and these are all gases. You can see generally that's terrible writing. You can see generally in a particular diagram that something is a gas if it's just spread out evenly through the whole container. And then it's producing, you don't actually have to write this equation, it's just sort of maybe helpful. Okay. Producing CO2 gas. And H2O, in this case, also seems to be a gas. It seems to be floating around. And there's a leftover methane as well. Yeah, almost forgot that part. This is a classic example of a combustion reaction. Joy is going to be talking about all the different types of reactions tomorrow. This is one of them. Oh, I was supposed to do this. I did it in the wrong place. We're just going to move this whole reaction. I'm sorry. They want you to write the balanced reaction. This part, yeah, this is okay. This is a little bit of a mess. Sorry, everyone. We're writing this equation and then they want us to balance it as well. Rude. All right. So they want us to fill in the coefficients here. In this case, because they gave us these diagrams, when you have a diagram like this, they will balance it. So you'll see there are the same number of each type of atom at the beginning as the end. So we can just like straight up see that there are 4 oxygen molecules and there are 3 methane. And then that reacts to produce 2 CO2. 2 CO2, 4 H2O, and a single methane. So we'll talk a little bit more about particulate diagrams in other contexts. You'll see the molecules. Sometimes you'll see arrows, little like movement vectors that display how quickly the molecules are moving and in what direction. That will often indicate like how much kinetic energy they have or whether they're gases or liquids or solids. If you see a liquid, it'll probably be like in the bottom half of the container, or a solid, you might see a lattice structure of like different atoms in like a nice grid or something. They're pretty easy to interpret most of the time. It's like a picture of the reaction that's going on. I trust that you guys will do all right with the particulate diagrams. They want you to do one last thing down here, which is draw a particulate diagram for this reaction. You have 1 diatomic nitrogen reacting with 3 diatomic hydrogen to produce 2 NH3 ammonia gas molecules. So all these should be gases. And yeah, you can go ahead and do that. Draw a little box for the reactants and a box for the products and fill them in with the correct number of each molecule. Maybe, I guess I could just add it to the end of the video. I don't know.
Yeah, because there's like 10 minutes, but we should probably get this uploaded before the period ends.
Okay, yeah, you can just take the computer and do that part. Okay, hopefully you got something sort of like this. It is nice to draw the nitrogens as a little bigger than the hydrogens because they're bigger atoms. And key or no key, as long as you differentiate between the two, you should be good. Okay, we have some workbook practice problems to work through. A little bit of practice. No, not AP, just regular.
you're done with that, I'll get at it.
Yeah, go ahead.